All right, moving along to z-scores. Hopefully I don't lose you if I haven't lost you already. So, z-scores and U. Remember, we have a theoretical normal curve, right? It looks like a bell curve, just like this. It is unimodal, meaning it has one mode, right? So it only has one hump. It's symmetrical, right? It's the same on each side of the halfway point of the median. It's not skewed, meaning that there's not one side going too far to the other. And also the mean, median, and mode are all going to be the same value in a theoretical normal curve. And remember, with this normal curve, we can use that 68, 95, 99.5 rule, and we can be relatively certain that 68% of our sample is going to be within one standard deviation of the mean. 2 standard deviations of the mean encompasses 95% of our sample, and 3 standard deviations away from the mean encompass about 99.5% of the sample. Sometimes you'll see it differently with like 99.7. Just sort of ignore that. We're going to go with 99.5. Doesn't matter why. So, right, look at this, right? Think about it. How often do we actually see a normal curve? Probably not super often, right? Don't worry about that. We have a theorem and a theory that we're going to talk about later on that will help explain why we can use this normal curve and this normal distribution, even when there's maybe not a normal distribution. We'll come back to this. But again, just for the point in time being, let's just assume that we are working with normal curves always. Right, so again, right, if we look at our normal curve, right, then that tells us, right, that the distances on our horizontal axis are always going to cut off the same area, right? So if we are halfway in the middle, right, if we have a middle point right here, that tells us, right, that half is going to be on the bottom and half is going to be at the top, right? And we can use this property to describe areas above or below any point, right? So I don't just have to look at the median, right? I can pick a score right over here, and I'll be able to calculate using my z-score what percent of the population is below that score and what percent of the population is above it. So if I have a group of 1,000 women and their average height is 64 inches, and I tell you the standard deviation for that is 3 inches, before we go into z-scores at all, right, let's just think about what we know about that 68, 95, 99.5 rule, right? So how many people, right, in theory, will be between 61 and 67 inches, right? Well, that's one standard deviation away from the mean, right? So 64 is our mean. Subtract 3, right, it gives us 61. Add 3 gives us 67. 68% of all people, right, of all women in this sample will fall within, right, that 61 to 67. So if I ask you for how many people will be in between that, right, you have 1,000 people, it encompasses 68, right, percent. So what's 1,000 times 0.68? It's a good question, isn't it? That's right, that should be, right, math is not my strong suit, y'all. Right, 680. Okay, now I know what I'm doing. So next, right, between 58 inches and 70 inches, well, that just adds one more standard deviation, right? So that means that now I'm 2 standard deviations away from the mean. So if I have 1,000 people and 95% of them fall within those, right, I know that those are within 2 standard deviations, I'm going to do the same thing again, right? I'm going to take my 1,000 people, I'm going to multiply that by 0.95, right, my proportion, and that means that 950 of them should be between, right, 58 and 70 inches. That's 2 standard deviations away. Do that one more time, right, between 61 and 64 inches, right? So that's only 1 standard deviation away. That's only 1 standard deviation down, right? So we think about a normal curve, right? We think about in the middle, right, 1 standard deviation away, 68%. So that's on both sides. But if I'm only looking for one side, that means I have to cut that 68% in half, right? So that means that 34% will be within that 1 standard deviation, right, below the mean. So, right, 38% times 1,000, what does that tell me? Right, about 380 people will be between 61 and 64 inches. And then how many people will be taller than 73 inches? 73 inches, right, is now more than 3 standard deviations away from the mean, or like 3 standard deviations, right, above. 73. So then that tells me, right, 99.5% of all people are within 3 standard deviations. So that means I have 0.25 on each corner that don't fall into the mean, right? So 0.25%, 0.25% is going to be 0.0025, right? This is why it's important to remember the difference between proportions and percents, right? We want to make sure that we're paying attention to that decimal place. So, right, 99.5%, right, that means that's 0.995, which means, right, that there is 0.0025, right, that is left on each side. So that tells me 0.0025 times 1,000 gives me 2.5 people. So, right, I would expect that somewhere, right, around 2.5, right, that's 0.5%. Hold on, just let me check myself real fast. 0.5%, divide that by 2, right, divide that by 100. Yep, so that is 0.0025, right, on one side. Right, it would be 0.005 if I was looking at both sides. So because I'm only looking at one, right, then it is 0.0025 because I take that 0.5% and I split it in half. Right, so that gives me 0.0025. I multiply that by 1,000. Again, I get 2.5 people. So I would expect only about 2, possibly no more than 3, to be taller than 73 inches out of the 1,000 women that I have in front of me. Right, so this is sort of what we're going to be doing with the Z-score. We are going to be figuring out, right, what percentage, right, what is the area, right, below our score or above our score or between 2 scores, right? So to find the area, right, which we're going to think of as the proportion or the percent of cases either below or above our score, right, we are going to first have to compute a Z-score. Right, and so our Z-score is going to change our raw score, right, whatever number it is that we are working with, and that's going to standardize it. And when it's standardized, then we can apply it to the normal curve. Again, we will get to the explanation of why we can use the normal curve, kind of, but it's more theoretical, right, and mathematical theoretical. So don't worry about that. Don't even think about it, right? So what we're going to do is we're going to change that raw score to a standardized score. When it's standardized, then we can assume the curve is normal. And then we can sort of guess, right, how many people are going to be above or below whatever score it is. So this is going to tell us, right, how many standard deviations either above the mean or below the mean a given score is. So to find the Z-score, right, we take our raw score, we subtract the mean from it, and then we divide it by the standard deviation. It's a super simple formula, right? It doesn't take a lot of steps, and I will almost always give you the mean and standard deviation or ask you to calculate that before you get to the Z-score. So you'll do this on your homework, right? You'll find information, right, about this data set. You'll tell me the mean at some point. You'll tell me the standard deviation at some point. And then when I ask you for the Z-score later on, you've already done almost every other step, right? If you get a Z-score that is positive, that means that it is this many standard deviations above the mean. If you get a Z-score that's negative, it means it's that many standard deviations below the mean. Okay, so if we get a Z-score of 0, that means congratulations, you are the mean, right? You are the average. So yay, I'm average, right? So positive Z-score means it is bigger than the mean. If it is a negative Z-score, it means it is lower than the mean, okay? So if I tell you that I have a data set, right, and the mean is 4, the standard deviation is 5, and I want you to find the Z-score for a score of 20, right? So all you would do is you would take 20, right, which is the Z-score, the score I want to know about, right? You take a Z-score of 20, right? A score of 20, subtract 24, right, which is my mean, which is the formula, right? And then I divide it by the standard deviation of 5. That gives me negative 4 over 5, which equals negative 0.8, right? So that tells me if it's negative, right, that score of 20 is below the mean, which we can see on our slide here, right? That the mean is 24. So if a score of 20, we want to know what the z-score is. That should assume that that's going to be a negative number, right? Our z-score will be negative because we already know that score we're picking, we already know it's below the mean. Right, so a z-score can be negative, it can be positive, and when it's negative, it tells you it's below the mean. When it's positive, it tells you it's above the mean. Right, so when we did this is telling us that the score of 20 for this data set is going to be negative 0.8 standard deviations away from the mean. Right, so we could check ourselves. Right, so we could do negative 0.8. I'm going to do it on my calculator with you. Right, so we have negative 0.8. How do I make it negative on my phone? That's a good question. Oh, there it is. There's my plus and minus. Negative 0.8, right? That is that many standard deviations. So our standard deviation is 5. So I'm going to take negative 0.8. I'm going to multiply that by 5. That tells me negative 4. That tells me, right, that my score is 4 less than the mean. Well, that makes sense, right? That's exactly what we see. So why would we do this to a z-score? Like, why would we take one score and turn it into a z-score? We do this so we can standardize them, right? So we can use that normal curve distribution even for, right, populations that might not have a normal curve, or samples that might not have a normal curve. This also allows us to easily compare populations with different means and different standard deviations. So if you remember from the Crash Course Statistics video that I had you watch, one reason we might want to do this is so we might want to compare somebody who took the ACT versus somebody who took the SAT, versus maybe somebody who took the GRE, right? How do we compare these scores, right? They're not on the same, right, measurement scale, and right, the standard deviations are different. So how do we know, right, if someone scores a 23 on the ACT and somebody else scores a 2100 on the SATs, how do we compare those two? Well, we have to standardize them, and that's why we would use a z-score. We also use this because it tells us we can find the area either above the z-score or below the z-score, which will tell us then the percentage of values above or below the value that we're examining. Right, so similar to what we were doing in that slide back here, we're looking at, right, how many people are going to be above or below, right, within this. It's the same thing. We're just not relying on this like 1 standard deviation versus 2 standard deviations versus 3 standard deviations. Right, now we can play with all sorts of things. So you are going to go to this website that is z-table.com. Right, so once you get your z-score, you need to figure out what that means, right? The z-score by itself doesn't tell you a whole lot. So we have to use this chart. So this is the easiest chart that I found to use. So z-table.com. All right, so this example is looking at a z-score of 1.09, right? You do your calculations, you get a z-score of 1.09. So first you're going to go to the left side of this column, right, where you see z. It says 0.0, 0.1, 0.2, right? And it keeps going on. You'll see it when you get to the website. So it just keeps going on. So the first thing you want to do is you want to find the first part of your z-score. So if my z-score is 1.09, I am going to look for 1.0. And then if we go up to the top, this is going to be, right, our 100th decimal place. So then I'm going to look for 0.09 because then that is 1.09. Right? If my z-score was 1.19, then I would look right here for 1.1 and then 9 for the 100th place. Right? So I have a z-score of 1.09, so I'm going to look right here first, and then I'm going to follow it all the way over until I get to 0.09, which gives me, right, my hypothetical z-score of 1.09. Then it tells me a proportion, right? It tells me this number, 0.8621, right? What does that mean? Well, that tells us the proportion of people who fall below our score, right? So for that hypothetical, if I get a z-score of 1.09, then that tells me that 86.21% or 0.8621, the proportion, right, that the proportion of people who are going to have a score below mine, right, is going to be 0.8621. Or I can also say that 86.21% of all other scores are going to be beneath mine. Right, this is going to be helpful, right? I remember thinking about SAT scores, ACT scores, GRE scores, all of that, right? This is going to be handy information, right? Because this is how we can tell, right, how well we're doing compared to other people, right? So if I find out that I'm in the 86, right, that 86% of people did worse than I did, that makes me feel pretty good, right? Right, I'm in the top 14% of all people then, right? And I'm going to feel pretty good about that. So, right, when we look at this Z-score table that I have for you, that I provided, is going to only tell you what is beneath your Z-score, right? So that is it's going to require a little bit more computation if we want to know maybe who's on the other side, right? How many people did better than us? So, right, the numbers in the chart, like I said, are proportions, right? Proportions are always going to be between 0 and 1, just like percentages are always between 0% and 100%. But we're looking at proportions. So this is before we do that 100 times 100 and add the symbol, right? Proportions. So this tells us the proportion of people below our score. But if we want to know the proportion of people above our score, we simply subtract the number that we find in the chart from 1. And then that tells us how many people are on the other side of us, right? So again, if our Z-score is negative 0.8, like it was in that first example, right, the chart then is going to tell me, if you go to the chart, it will tell you that the proportion is 0.2119. So that means that 21.19% of all scores are lower than the 20, right, than my 20. But if I want to know how many people are above me, right, then I just take 1 minus the proportion, which is 0.2119, and that gives me, right, 0.7881. So then I can turn that into a percentage, right, by multiplying by 100. And that tells me then that 78.81% of all scores are going to be above mine in this distribution, right? So that tells me that I'm not doing so well on this one, right? I am only doing, right, there are only 21% of people who did worse than me, right? I'm not doing so great on this one. But 78% of people did better than me, right? That's what this tells me. So all I have to do, remember, if we are looking for what is above us on the Z table, right, then all we have to do is subtract that number in the chart from 1, and that'll tell us the other half of it, right, the other side. So right, that tells us about what's above us, what's below us. But what if I want to know what's between two scores, which is something that you're going to have to do for your homework, right? Tell me what is the proportion or percent or area between two scores. So what I'm going to do, right, is I'm going to calculate the Z-scores for both values, right? So in my example that I have here, I ask you the proportion of scores between 50 and 60 with a mean of 50 and a standard deviation of 10. Right? You don't need to worry about what scores these things mean, right? Because I've already given you all the information that you need to know. So to calculate a Z-score for both, right? Again, I'm going to follow this Z-score formula. So I am going to subtract my X value, right? Take X, and I'm going to subtract the mean from it, and I'm going to divide that by the standard deviation. So for a score of 50, right, what am I going to do? I'm going to take 50 minus 50, and I'm going to divide that by 10. That gives me a Z-score of 0. What does that tell me, right? Which we probably already knew. That is the average, right? That is the mean. And then I'm going to do the same exact thing for a Z-score of 6 to find the one for 60. So what am I going to do? I'm going to do 60 minus 50, and I'm going to divide that by 10. And then that gives me 10 divided by 10, so that answer is 1. Right, so now I have a Z-score of 0 and a Z-score of 1, and I want to know what percent or proportion is in between those two things, right? So I'm getting a phone call. Hold on. All right, he can wait. It's just my brother. So the corresponding area in the chart, right, tells me that for a Z-score of 50, for a Z-score of 0, right, which is what I have for my score of 50, right, then that corresponding area is 0.5. Again, that's going to make sense, right? It's the median. It's the middle, right? It's the mean. All of those things are true in the normal distribution. So if it's 50, if it's my mean, that means that half of people are going to be below me and half of people are going to be above me. But for a score of 60, right, my Z-score table tells me that my area is 0.8413, right? That means that, right, again, 84% are beneath me. And so I want to know what's between those two scores. So I think visualizing it might help us understand why we're doing this a little bit. So if we think about it, right, our one score, right, is right here, the 50, right, 0.5. And then, right, our other score for 60, means that 84% is going to be beneath us. So that means that it's somewhere around like right here. Actually, I think I can draw. Cool. So I already know, right, that 50, woohoo, that's a straight line. Pretend that's a straight line. This is fun. Okay, all right, so I already know, all right, 50% is beneath me for a score of 50. And then for my 60 score, I know that, all right, say I've got 84 here. So, all right, that's my 60. And I already know that 84% of people are beneath me. So, right, that is, right, whee. That's beautiful. I hope you can still tell what I'm doing. Right, so I know that there is overlap, right, between my red and my blue here. And so to find out, right, what is where the overlap begins and get rid of that, right, what am I going to do? Super simple, easy, right? I'm just going to take my bigger score, right, which is, right, for 60, it's my 0.8413. I'm going to subtract, right, my 0.5 from 0.8413. What does that tell me? 3.3413. So that means that, right, that is giving me the information that is right here, right? Boom. That was a much better job. All right, so then now I know, right, all right, what is green? Green is going to be, all right, that. So now I can tell you that 34.13%, or the proportion of scores in between those, are 0.3413. Again, I can easily turn that into a percentage, but I believe I ask you for a proportion on your homework. Please don't confuse them, right? A proportion is not a percent. They're close. They're talking about the exact same thing, but we have to do an extra step to a percentage. So this tells me, right, that the proportion of people who scored between a 50 and a 60, right, is going to be 0.34, right? That's my proportion. Or I can express that as 34% of people are going to have a score in between 50 and 60. Okay? Okay. So I think I have to erase all this because I think it's going to follow me along to the next slide. What does that do? Oh, look at me. Look at me go. It's cool. So areas, right? We can also think of these areas, right, as a probability, which is sort of how I've been talking about them, right? So if you think about probability, right, if I have a deck of cards, right, we all know cards, normal playing cards, right, there's 4 of each type of thing, right, and right, 4 suits, and then we've got 13 things in each suit, right, are 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, ace. Yes, right, we're not playing with jokers. I don't play with jokers. I know lots of people do, but we're not going to talk about jokers right now. Side note, anybody want to play some spades? Because I could use some friends to play spades with. But anyways, if I am looking for the probability that I'm going to draw an ace, right? I know that there are only 4 in the deck, and there are 52 cards in the deck. So what do? I divide 52 by 4, or 4 by 52. What does that tell me? 0.0769, right, is my probability. It's a proportion of cards in there that are going to be an ace, which again, I can turn into a percentage, and that will tell me that I have a 7.69% chance of drawing an ace. Pretty low, right? And similarly, right, I can use the area from a z-score table. I can assume the probability of a score being above or below that score. So if we go back to that original example, right, of the the mean being 24, the standard deviation being 5, and I asked for the z-score of 20, right? So the z-score of 20 was negative 0.08. So that means the area below that score is 0.2119. So that means if I were to randomly pick an exam, right, pretend those are exams, right, with weird scores, weird level of measurement, right, pull one out of that pile, that means that there is a 21.19% chance that the score that the whatever exam I pick out of the pile, all right, that the score is going to be below that 20. And therefore, right, I can flip that around. And that also tells me, right, that if I pick a random pile, right, exam out of that pile, that there's a 78.81% chance that the score is going to be above 20. right? So that is Z-scores. Right, it's super handy to tell us sort of where one score is in relation to all the other ones. And it is, right, somewhat simple in terms of calculating, but a slightly more, right, complex in terms of understanding and being able to apply these Z-scores, right, and to be able to, right, sort of interpret, right. So I know that if you go to the Z-score table website that I gave you, there's a Z-score calculator. Cool, right? Awesome. It's a simple calculation anyways. If you're too lazy to do that, right, yourself, then that's on you. You're really, all you have to do is report the mean, the value, and the standard deviation, which you got to type in there anyways. Like, you're not really saving yourselves any steps doing it that way, right? But really what I really care about knowing is, what does that mean, right? What does that Z-score mean? And so that website's not really going to be able to tell you how to interpret that data. So if you decide that that's how you want to calculate your Z-scores for me, you know what? I don't calculate Z-scores by hand, so I can't really tell you not to do that. However, I find that calculating by hand, talking through all this stuff, helps us be able to interpret this information later on. Because again, we're going to have SPSS do all the stuff that we're doing right now, right? That's what we're going to do in the lab this time, is have SPSS calculate Z-scores and things like that. So, right, this is really, right, asking you to make sure that you know how to do these things so that you know how to interpret these things, right? The biggest thing that really matters is if I tell you the Z-score is negative 0.08, what does that mean, right? So calculating the Z-score, kind of important, right? But most important is, what does the Z-score tell me? And the Z-score tells me, right, what the proportion of people below my score is and the proportion of people above my score. Remember, it is going to sort of standardize our curve, and it's going to help us be able to make more inferential guesses based on the information that we have. Right, it's going to help us sort of think about probability and percentage, right? What's our chance? What's the likelihood? So again, if you go back to that example of the woman, right, weighing, right, guessing, like you have to guess whether it's an apple or not an apple, right? That's on the scale from the crash course video, right? This Z-scores, right? They're going to help us, right? They're going to help us standardize the difference, and they're going to help us know, right, what's the likelihood, what's the percentage, what's the proportion of things that could be either below this or above this. And then eventually, right, this is going to help us determine what's significant, right? Is if there is something, right, there's a 0.5% chance that this could have happened randomly, then that's going to tell us eventually, right, that means that thing is significant, right? That there is something happening here that is statistically, right, doesn't make sense, right? We can't explain it any other way. So that if it's statistically significant, that means that something is happening here that tells us, wow, this is interesting, right? So if we talk about exams and things like that, right, and I look at everybody's exam score, and everybody seems to be falling along one place, right? Everybody's sort of clustering in the 60s and 70s. But then I have one student who scores a 98. Right. If I calculate their Z-score, right, look at all of that, and it tells me that the area below them is 0.99999. Right. That means that there is a 99.9999999, right, percent chance that somebody else, right, any other score is going to be beneath them. When looking at the mean and median and all these other things, right, and the range and the interquartile range, and I keep seeing this one super high outlier, right, that means something, right? That means that is statistically significant. There is a significant difference between that super high score and everybody else. Right. And so then that's going to lead me to ask some more questions, right? That might lead me to ask, well, did they cheat? Or is this like their third time taking this class, and the early stuff is super easy now because this is their third time getting it, right? That's still going to tell me something different is happening over here, right? It is statistically highly unlikely that this person who's scoring super high on the exam when everyone else is bombing it, as long as something's probably going on over here, right? And so, right, this is where we're going to leave it with Z-scores. Again, we're going to keep chugging along in our next unit. All of this stuff is going to build upon itself. So make sure that you feel good about this. Please, 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 please ask me questions. If you are confused, I can hopefully answer questions and explain things differently based on the questions I get. But I have to know where you're confused to know where to help you. So please, please, please reach out to me. I will probably in all likelihood extend our homework due date for this week, just because I'm a little nervous for some of y'all, right? Most all of us were on the struggle bus hard for homework for Unit 1. So let's make sure in Unit 2 that we are not on that same struggle bus. Right. I am going to keep that due date in Canvas for now. If I don't hear anything from anybody until Sunday, I'm going to assume that you guys are feeling pretty great about this stuff, and I don't need to extend the assignment. So please ask me questions, because chances are if you ask me questions because you're struggling, and lots of people seem to be struggling, then we're going to take Monday to talk this over a little bit more, and I will extend your homework due date. But if I don't hear from anybody, I'm going to assume that you don't have questions, and we can keep chugging along in the lab on Monday. So hope you guys watched all the way to the end. Please ask me questions. I am here always. Usually always. I will drop most things that I am doing to come help you with these things. But you got to ask me questions in order for me to be able to help you answer them. Okie dokie. Take care.